When the R value is larger, that material will have a greater resistance to heat transfer than a lower R number. So this guy's putting R19 in a 2x6 wall, but we know that a 2x6 wall isn't 6 inches thick. We know that it's 5.5 inches thick because 2x6 is the nominal dimension, and 1.5 inches by 5.5 inches is the finished or dress dimension of a 2x6. So this guy here is putting in R19 batt insulation. So again, bigger number is better. Vaughn asks, what is a nominal or normal R value used in houses? It's going to depend on where and the type of construction. Again, this guy here is putting insulation in a 2x6 wall. So in a 2x6 wall, we could put R19 insulation. More common still is, well, more specifically, 2x6 is on 24-inch centers. What's more common construction would be 2x4s on 16-inch centers. And in a 2x4 wall, we would be using either R11 or R19, or excuse me, R11 or R13 insulation. So typically in a wall, we're going to see something between R11 and R19. In the roof, we're going to see something between R38 and R49. So again, higher numbers for insulation in the roof. Because heat is going to tend to rise and flow out the top of the building. Also, the construction of the roof allows for more depth of insulation in the ceiling than it would in the walls. So we're typically going to see somewhere R38 to R49 in the ceiling. Does that answer your question, Vaughn? Hopefully you're still there. Again, the IRC, the IECC will specify the minimum code requirements. You know, we talk about it a lot more in the 108 and 110 classes, doing better than minimum. Okay, so here's batt insulation, R19 batts being used in a wall. Here is spray foam insulation. Again, this has some advantages. Spray foam insulation is good if you have kind of odd or irregularly sized or shapes that you're trying to insulate. Spray foam insulation will provide a substantially better barrier to air infiltration or air leakage than batt insulation. The downside is spray foam insulation is more expensive to install than batt insulation. Here's another insulation, rigid board insulation. You'll see rigid board insulation in a couple places. It might be used as a sheathing material on the outside of the house. So you can have insulated sheathing outside. You can have rigid board insulation in the underneath the floor slab to insulate underneath the slab in a basement. You can have rigid board insulation on the foundation wall. Those are all places where you might find rigid board insulation. In commercial construction, you're typically going to find rigid board insulation on the roof in a flat roof commercial building. Here is blown-in insulation. Right, again, this is a loose material, comes in bags, and then it's blown in. So this is an example of loose fill insulation in an attic. So in this case, I have much deeper structural members, so I can put in a lot more insulation to get to that R49 that the code is calling for. We're still in Division 7 here, right? So here's some examples of roofing materials. And let me just double check something here. How about that? I'm just making sure I got all my videos teed up here. Here are different examples of different roofing materials that might be used. Right, asphalt shingles are going to be the most common roofing that we're going to see in residential construction, where it's not a flat roof. Right, we may also see a standing seam metal roof. Some other things probably less common, slate or tile. Again, still in Division 7, siding materials, right? What are we going to put on the outside of the building? We're probably going to have some kind of vinyl siding or insulated siding. I always like wood siding, but wood siding requires maintenance and painting. Nowadays, people are using other sidings, vinyl or fiber cement, sometimes called hardy board, right? But a lot of different materials that we can use to finish or side the house, side the building. Okay, Division 8. Again, I snuck Division 8 into the lecture here. So Division 8 would be openings, windows, and doors. So how is glass made? Glass is made by what I'm going to show you here. So hold on a second. Let me get that teed up. I should have done that during break. My apologies. So float glass, most common type of glass, as you'll see in a minute, a ribbon of molten glass comes out of a furnace and floats on a bath of molten tin. So that's how we make float glass. So let me show you what that looks like here. Where did we go? Come on.
This local access message is...
Okay, so sorry about that. Let me show one more video here about tempered glass, and then we'll go back to the
Fully tempered glass is subject to a special heat treatment. Fully tempered glass is subjected to a special heat treatment in which the glass is heated to about 680 degrees centigrade. After heating, the glass is cooled rapidly using air jets to cool it quickly and uniformly. This process is called quenching. After glass is tempered, it is up to 4 times stronger than annealed glass of the same thickness when exposed to uniform static pressure loads. If broken, the entire piece will fracture into many cube-like pieces, which are less likely to cause serious injury to people. Most architectural glass can be tempered. Once annealed glass has been fully tempered, it is not possible to alter the appearance of the piece. For instance, holes, polished edges, and notches must all be completed before the glass is tempered. If any additional processing is attempted after tempering, the piece will shatter. The tempering process does not affect the color, clarity, chemical composition, or light transmission of the glass. The only physical properties that change are improved bending capability and tensile strength, and improved resistance to impact and thermal shock.
okay, so that was tempered glass. They used a couple different terms there while I find my file again. Right, float glass was the process that was used, the molten glass floating on a bath of molten tin. There was some treatment of that float glass done to produce annealed glass, and then an additional heat treating process turned that annealed glass into tempered glass. And with that, let me go see if I can find the rest of my... Okay, so again, we saw what float glass production looks like. Right, so from that we can take our annealed glass and bend it, or we can produce various types of safety glass. We just saw tempered glass. You know, it has much higher resistance to breakage. Laminated glass would mean that a couple different sheets of glass are put together with a material in the middle. Or wired glass, again, sheets of glass are put together with some thin wire in the middle. These are all examples of safety glass, right? We have safety glass in our storm windows in our houses, right? So our storm door has tempered glass in our house. So if you accidentally stick your arm out while the door is closing, right, either the glass won't break, or if it breaks, it's gonna break in those regular pieces that we saw in the video there about tempered glass. Insulated glasses are where we put various layers of glass together, sheets of glass together with an airspace between them, and that combination of glass and airspace improves the insulating value, right? Makes the window more resistant to heat flow, reduces the U value of the glass, right? Remember, U value of windows and doors, lower U value is better. We can also put patterns in the glass. We can color the glass and have stained glass. Right, we just saw that video on tempered glass production. So these are examples of insulated glass, either a double glazed or triple glazed unit. So again, we have sheets of glass with an airspace between them and a spacer that establishes that dimension. Desiccant means you have some material in there that's going to absorb moisture. So we don't want that airspace to fog up, because then you can't see out of the window as well. And there'll be some kind of sealant to keep that airtight and keep the moisture out. And again, a triple glazed unit, similar things. So again, when we're trying to make buildings that are more energy efficient, use less energy, we're going to increase the R value of our wall insulation, right? We're going to use R19 instead of R11. We're going to go from, instead of a single glazed window, we'll go to a double glazed window or maybe a triple glazed window, right? All things that we will do to make buildings more energy efficient. Again, examples of patterned glass, right? I have patterned glass in the bathroom of my house, right? It's a regular double hung window, but the glass is patterned so people don't see inside when I'm in my bathroom, right? Right, we can also have stained glass, right? In this case, we have, this is a stained glass window from probably one of the Frank Lloyd Wright houses, right? So we have pieces of colored glass put into lead or zinc cames to produce a decorative effect. Right, we just talked about high efficiency windows, right? We're going to go from double or triple glazed windows to reduce the heat loss to make our buildings more energy efficient. Meets code specifications, right? Again, in our IRC or IECC, in our I codes, our model codes, there are going to be stipulations for U values of windows. If you're in Miami Beach, the code will stipulate how well the window keeps the sun out, the solar heat gain factor. Right, so again, here's an example of a window with insulating glass. Right, this happens to be a window with aluminum on the outside and if I'm looking at correctly, wood on the inside. Let's go to Division 9, finishes. Finishes are the surfaces, visible surfaces on the inside of the building. Right, the carpeting, the wallboard, tiles, paints. Typically those finishes will be spelled out in a room finish schedule or in the specifications. Right, so what's a common finish material? A common finishing material is gypsum wallboard. Right, so gypsum is manufactured, as you'll see on the next slide, with a processed mineral that's put together between two sheets of treated paper, often in 4x8 sheets, so it could be bigger, 4x9 or 4x10. So gypsum is, right, we take, kind of similar to the production of cement, we take raw materials, we crush them up, we grind them, we process them, and then we pour them out between layers of paper and Number 11 is a kiln there. We bake them. Yes. Yeah, I think those terms are synonymous with each other. Wallboard or gypsum board, gypboard, GWB, they're all typically talking about the same thing. Right, gypsum, GWB or gypsum wallboard has become the common way that we provide finish in frame construction. It says due to the ease of installation, familiarity, fire resistance, non-toxic, sound attenuation, right? That's become kind of the go-to way that we finish the inside of our frame construction, right? In the older house that I live in, right, 100-year-old bungalow in Oak Park, right? My walls are plaster. That's how we typically finish the inside of houses 100 years ago. But nowadays we don't do that anymore. We use gypsum wallboard. The house that I live in is plaster on wood lath. Sometimes we had plaster on metal lath. Then after World War II, we kind of switched to GWB or gypsum wallboard. How thick is drywall? I put this together here with examples. Probably in residential construction, 1/2-inch drywall will be the most common. You might see 5/8 drywall. You certainly see 5/8 drywall in commercial application. You might use 5/8 drywall if you're going to 24-inch stud spacing. You're likely to go from 1/2-inch to 5/8-inch drywall to add a little bit more rigidity to that wall that's framed with 2x6s at 24-inch centers rather than 16-inch centers. Some other finished materials: ceramic tile, glazed or unglazed on floors or walls, mosaics, quarry tiles, right? A wide variety of tiles that can be used as finished materials. Here's an example of the tile guy layer, the tile person, tile layer, putting down the ceramic tile in a bed of grout, or actually in a bond coat. And the grout will go in the middle. Remember that bond coat and grout are also made from cement, just like the concrete is. The mortar that we saw with masonry units is also made with cement, just different ways of mixing up that material. So again, that ceramic tile is going to be laid in a bed of a bond coat. Right here's ceramic tile on the wall. We could also have mosaic tile. In this case, it'll be a sheet of smaller pieces of tile that are in a backer where the sheets go down together. Here are quarry tiles, so this will be, stones that are cut and dressed to a specific size. Right, ceramic tile is set in a variety of things, either Portland cement or latex or an epoxy. And then we grout between those tiles with some kind of mortar. And here's some examples of, I think the detail is in the book on page on figure 723 on page 124, right? How those tiles are set in the bond coat and grouted between them. Right, we put the ceramic tile on our plywood subfloor. Right, we saw the plywood being used in that video on platform framing. Or let's say we're in a commercial building where the floor slab is concrete. We could have set our ceramic tile and a bond coat over that concrete slab. And some examples of symbols that are used to denote or designate the various materials. Any questions on materials, folks?
I had a
oh, yeah, go ahead.
So, when you talked about the finishes, you said that the finishes will be either specified in the specifications, or there was another word that you used that I missed.
Yeah, a room finish schedule. So you might have a room finish schedule in the drawings. Remember, our construction documents typically consist of drawings and specifications. So you might have a sheet toward the back of your drawings that has a room finish schedule. So it'll say, dining room shall be this, right? So you may see a room finish schedule, or you might see it called out as a note on the drawing, or you might see it in the specifications. Does that make sense?
Yep, thank you.
Okay, you're very welcome. Any other questions? Okay, we'll go, since we got a few minutes left here, I'm actually going to go back. I'll play that. Got it. I'll go back and play the video on steel making in 1944. I wasn't quite sure how we would work out with timing here, which is why I didn't play it before. So let me go back and do that. Hold on here.
This is my hometown. It's called Youngstown, and it's in the state of Ohio near the Pennsylvania boundary. In Youngstown, we make steel. We make steel and talk steel. I guess it's the same in Sheffield, England, or that place the Russians built in the Urals, Magnitogorsk. I'd like to tell you something about how we make steel here. Look down any street in town, and you'll see the mills at the end of it. There are 25 miles of them along the Mahoning River, and today they're busy day and night. Every 8 hours, the shifts change. 15,000 men to the shift. The men going to work can see the freight trains bringing in the raw materials: iron ore, coal, and limestone. This is the ore. It looks like dirt, but in a few weeks it'll become part of a ship, a tank, or a gun. And in peacetime, an office building, a bridge, or a dam structure. An overhead crane picks it up and carries it over to the skip hoists, which take it up to the top of the blast furnace. In the blast furnace, the boys smelt the ore into iron, the first step in making steel. Molten iron comes out at 3,300 degrees. slag comes up to the top like cream in a pitcher and goes out the other way. That's Johnny Chonko on the snort valve controlling the blast. When things get too hot, he's got to think quick and move quicker. Peter Zeman's the blower, head man on the ship. He tells him when it's time to stop the flow. This is the open hearth where the molten iron from the blast furnace is mixed with scrap iron and the two purified into steel. I remember the first time I saw it, the size of the place, the noise, the sirens wailing when the big stuff moved overhead, and the heat hitting you like a solid wall. It's something you don't forget. These boys are slagging, lining a furnace with dolomite. This protects the wall of the furnace against the extreme temperature. Down the line, Bob Wentworth is charging scrap iron, scrap that came from farms, backyards, and attics all over the country, collected by school kids and housewives to do their part in the war. Next door, Tommy Hughes is giving one of the furnaces a drink of hot iron from the 35-ton ladle. This iron is fresh from the blast furnace. In the open hearth, the steel's nearly finished. The first and second helpers take a sample. Mike Kubinski's the first. Earl Strong is his assistant. Mike's people came here from Czechoslovakia. Earl's ancestors came from England in the 17th century, when there wasn't much to America but a few colonial villages along the coast. By inspecting samples of the molten steel, the boys could tell exactly when the furnace should be tapped. The open hearth gang ravels out the hole in the rear of the furnace and lets the steel out, roaring and spitting at 3,000 degrees. The pit gang dumps in alloys to give it the special qualities they want in this batch. This ladle weighs 100 tons, but the overhead crane handles it like a toy. Lifts it over to a line of ingot molds where it's tapped off. We call this teaming. Just to be on the safe side, another test is made to be sure that the alloys have been added in proper amounts. The ingots are carried over to the blooming mill where they get their first shaping. rollers squeeze the ingots down to a tolerance of a 1/16 of an inch. George Bannon and Clarence Kinney control the operation from the pulpit. They've been doing this together for so long, they work like one man with 4 hands. When the ingots flatten to a slab, Fred Ingram takes over. He cuts a slab with hydraulic shears under many tons of pressure. Fred's a shop steward for the union, which has an agreement with the mill. He represents the workers on the plant's labor management committee. These days, they're discussing production problems. We've got the machines, like this one in the hot strip mill, where in one continuous operation, a slab of steel is flattened into a sheet. Each roller operates at a different speed, synchronized to handle the slab that's growing longer and thinner and moving faster all the way down the line. This is it, steel. Only a few hours ago, it was iron ore. Now it's finished and on its way to become a part of the new world it's building. We've proved we can lick production problems. We've got the equipment, the science, everything it takes to get the job done. But when the war is over, we're going to have other problems. We know about that in Youngstown. We've had it here before. There were times when there was no smoke in the sky. The mills were quiet. The street full of men, angry, questioning, wondering. We're beginning to understand that these things don't just happen in one place, they happen everywhere. We're thinking that all this production all over the world that's doing such a job in a war can do a job in peace too, if we can just learn to work together.
Okay, I found that one kind of interesting. Certainly the basic process of steel making hasn't changed that much in between 1944 and the peak of World War II and whenever that video from U.S. Steel was made. The process is about the same, but a lot more people putting themselves in harm's way in 1944 than currently, right? It seems like a pretty unsafe business to be standing there next to 3,000 degree liquid. So not a job that I would necessarily want to do. Anyways, that's what I have for tonight. We will have a quiz on next Tuesday at the beginning of class, primarily on materials. Yeah, a lot more people were required to make steel back then than today, right? We have the Steelworkers Union probably had hundreds of thousands of members, and now it's probably tens of thousands. So yeah, the steel business is a lot more automated than it was in 1944. So again, we'll have a quiz on Tuesday, primarily on the materials on units 7 on materials. I would ask you to read chapter or unit 5, primarily the part about sketching we don't necessarily have to talk about, but toward the end of unit 5 where it talks about orthographic projections and how we turn a three-dimensional building into a set of two-dimensional prints to basically visualize how that happens would be good for you. Good for you guys to work on. Any other questions?
So it's just primarily chapter 7 that we study for the quiz?
Yes, that is correct. Yep.
Awesome. Thank you, Mr. Becker.
Yep. You're very welcome. I'll try to sneak a few curveballs in there, though. I always I always want to try to stay one step ahead of my students, or at least to provide a meaningful challenge. So, but yes, Unit 7 on materials. And again, I will, let me stop the recording here. I will